Hi, my name is Eric Palmer, and I'm the team lead for the ENMA 490 capstone, and this is the HDPE EVA composite team. So the scope of our project is to try to create a new material from recycled EVA and HDPE, as about 30% of the US thermoplastic produced material is HDPE, yet only 5 to 6% of all recycled material in the US gets recycled. So our goal is to see if we can try to create a new material with desirable properties that combines the strength of HDPE and the toughness of EVA into something new that creates no waste and is just made completely from waste. So the basis of our technical approach is that thermoplastics in theory are infinitely recyclable. You can melt them down, you can press them and mold them, shape them, and anything you really want. That being said, the reason we chose recycled HDPE and EVA is because they are relatively easy to press, mold, and shape once you heat it up, and we want to be able to create a new material from them. The basis of the project relates to composite design, which we are combining two materials and taking the properties from both, and that new material is going to hopefully give us the best of both worlds. Composite design is so important is because both materials have low surface energy, so it's going to be the design that dictates a lot of the properties, as well as the geometry of the design that will dictate how strong and how flexible the material actually is.
Our materials were donated to us by the Prince George's County Material Recycling Facility. They were able to donate us containers of HDPE, both the natural and dyed variants they have. Natural being containing no additives, something you would see in like a milk carton, and then dyed, containing dye, something you would see in a detergent container. After we received these materials, we had to clean them. This included removing other materials attached to the container, labels, and sticky things such as glue. We did this just by mostly physical abrasion, as well as a combination of soapy water and alcohol. Once we had our materials cleaned, we had to then go shred it at the Terrapin Works Advanced Fabrication Lab. We shredded it in order to get it into a more processable material. We did this using their industrial shredder, which had contaminants of PLA, so that presented us a problem where we needed to sort a mess of HDPE, seen here in the green, with little contaminants of orange PLA. And we did this using a gravimetric process, which pretty much included us dumping the two materials into a container of water. Since HDPE has a density less than water, it floated to the top, and since PLA is more dense than water, it sank to the bottom. And then just with a little bit of stirring, we were then able to scoop out the HDPE from the top, giving us a clean, pure material. We still had some issues with small particles of PLA attaching to the surface of the HDPE, but we were able to consider that a non-factor, and that allowed us to continue forward.
As for the processing of our material, we decided to use a heat press to get even sheets so that we can make our composite design. So what we did was we individually used our recycled material to press out first HDPE sheets and then EVA sheets using a heat press similar to this, where it's two parallel plates that were heated and then provided equal pressure to our material. EVA was at a temperature of around 120 degrees Celsius with a low pressure under 1,000 psi, whereas HDPE had to be cranked up a little higher to 130 degrees Celsius with around 10,000 psi. Once we had these sheets, we were able to process them into our different types of fibers. So for our HDPE sheets, we either cut circle holes in them using a hole punch. We cut out the negative fibers, which were just fibers with, which is a sheet with just fibers cut out through it. And then with those cuts, we had our positive fibers, which were just the fibers with no surrounding HDPE. With this, we were able to make our composite by stacking one layer of EVA, then our HDPE sheet, and then a thick layer of EVA, and then another HDPE sheet, and then our final layer of EVA. This ensured that there was bridging across the HDPE sheets through the holes in our composite, and that way, since HDPE has a low surface area, it was able to maintain in the composite and bond fully.
To test our samples, we use tensile testing to measure the tensile strength, yield strength, elastic modulus, and toughness of our samples. We cut our samples into dog bones to pull inside the tensile testing machine. From our samples, EVA had the lowest elastic modulus and HDPE had the highest elastic modulus, while HDPE had the lowest toughness and EVA had the highest toughness. Our highest performing sample was the negative fiber sample, in which it surpassed the toughness of the EVA, but also maintained the high tensile strength of the HDPE. Our holes composite, however, had the closest approximation to the theoretical elastic modulus. Finally, our positive samples had similar tensile strength to the HDPE, and similar elastic modulus, but they had much lower toughness.
So in the end, we made an effective recycled EVA HDPE composite material with higher strength like HDPE and higher toughness like EVA. The original intention of this work was to make a insole, recycled insole for a shoe, and this is our shoe. While it's not a perfect application for a shoe, the composite that we actually made has some interesting potential applications. And our example application is something like a stretcher, where you might need some strong fabric to hold your patient. One of the reasons for this is that EVA has been commonly used as an antimicrobial material and could be used for similar purposes in the future. We want to thank Dr. Breiber, Dr. Bonenberger, Dr. Fanev, Dr. Ponce, Dr. Kofinas, Noah Hoppus, and the PG County Materials Recycling Facility and Materials Engineering Department for making our project possible. And lastly, we want to shout out Dr. Coates for helping us all along the way.